Okay, so this is motivated very much by the idea of collective adaptive systems, and I'll explain just what I mean by that. I'll do a quick recap of quantitative analysis and what it means in this context, and why it's particularly difficult to model collective adaptive systems. So in particular, why a language like Pepper just wouldn't do it for us. So why we have to design a new approach. And the new approach is a language called Karma, which is collective adaptive resource sharing Markovian agents. You might have gathered in ProSage, but there's a lot of work on choosing acronyms and finding the right ones. So we have this language Karma, and I'll explain the language, particularly emphasising the communication there, which is quite different to Pepper communication, and we'll look at a smart taxi example. So collective systems, so they occur a lot in the natural world, so these are bees, fishes and birds respectively, and the idea is that you have agents whose perception is quite limited, that they can just see their neighbours more or less, and they have certain simple rules of how they react to those neighbours, but through those rules you get a collective behaviour that you perhaps wouldn't have anticipated if you looked at the individuals. So it's sometimes called emergent behavior as well. But it also happens quite a lot in the man-made world, so traffic jams are a sort of example. These are swarm robots, where people use robots to investigate certain areas, so particularly they're envisaged for using in disaster relief areas. So they have a limited scope of communication, but then collectively they can cover quite a wide area. And the map at the bottom is back to the old idea of SIR models. That's actually the spread of the H1N1 virus. And this is very much a collective dynamics, because depending on the information that people have about the disease, they will behave differently, which alters the spread of the disease. And this is the general idea we have of collective systems when we come to the man-made world, is it's often associated with smart systems, because people's behaviour, computing elements' behaviour changes because of information they get about how the system is acting. So this is sometimes called an informatic environment, because it's very much human in the loop kind of idea, that you've got some agents, some aware of each other, some not, but you've got information about the system which alters their behaviour, and they often adapt to the environment as it's going on. So from a more abstract point of view, we can think of this as a system made up of different entities. Different types here are represented by different colours and different orientations. So each entity will have its certain properties, possibly objectives. Certain humans in the system will have objectives or goals they're trying to meet, and certain actions that they're capable of doing. And then these combine to create collective behaviour. And when we look at it as a system as a whole, we might see a certain tendency. So here perhaps the tendency is that the agents are kind of heading up to the right. And when that information sort of permeates through the whole system, more of them may align with that, so they may try and fit in with the system. So we have this feedback that the behaviour of the system is influenced by the individuals, but the individuals are then also influenced by the system. And this all should happen without centralised control. So for these informatic environments, we're often thinking of sensors that are embedded into buildings, etc. It's not the case that somebody is really telling them, now is the time for you to change your behaviour. And moreover, the conditions change within the system. Human intervention, as I said, may not be appropriate, and so we expect the system to just change itself or adapt autonomously. So Robin Milner, who invented CCS, one of the process algebras I mentioned, also coined the phrase of the informatics environment. And he thought of this as this idea of sometimes called pervasive or ubiquitous computing, where computing elements become really just invisible to people in the service. And we have this in a sense with the internet now. Everyone expects Wi-Fi, expects to be able to do things. We don't actually even think about the contact points or whatever. It's just there. And the idea is that things will become even more so as we get smart homes, etc. And it becomes actually even more important than previously that we do good modelling before we deploy systems to understand their behaviours, because these are things that are happening to people without their awareness. So they're often made up of a large number of computing elements that collaborate to sort of meet the human need. And we see this in, as I mentioned, smart buildings earlier, we see this in hospitals, for example. We also see it when you hear about smart cities. And I'll talk a little bit about what we might want to do in smart cities, where we have things like smart urban transport systems, and this is a classic case where we provide information to users which might alter how they behave. So they may be waiting for one bus, they see it's going to be heavily delayed, they take a different bus, which changes the loading on the system, which may then alter the timing of the bus they took. So there's a lot of very complicated feedback in these systems. Another one is smart grid, electricity generation and storage. So here, what do our problems, our classic performance problems look like? So the capacity planning might be how many buses do I actually need to have in my system to keep it running at peak time with a reasonable service. Bike sharing systems, which in my group we've done quite a lot of work with. We look at things like what capacity do I need to have at bike stations, or what policies might I have? Because what I want to do is minimise the movement of bikes by trucks. So bike sharing systems tend to keep this quiet, but often a lot of work is done redistributing bikes. So this is Paris. People in Paris don't like cycling up hills, so what they find is that people are very happy to take bikes from the top of the hill, but they return them at the bottom of the hill. And so they have to use lorries quite a lot to transfer things around, and you can look at policies, scoping. And what they're doing, which is quite interesting, is incentives. So they give different pricing if you will take your bike back to an empty bike station rather than one that's half full. And we can model all those things. And then in the smart grid situation, what we're looking at is tuning. So again, you're trying to design a strategy of how you balance the supply and the demand, because you must always keep those within a certain range. And with renewables, that's incredibly difficult. So as we saw, Markovian-based discrete event models, which are the Markov chains, have been applied for performance analysis of computer systems and communication since the early 20th century. I forgot to mention the first application was Erlang's loss formula. Erlang was a Danish mathematician, and he was looking at how many actual physical wires and operators you need in telephone exchanges in the days where somebody would pick up the receiver and say, please connect me to, I don't know, Copenhagen 156, and somebody would physically plug a wire in, and the Danish phone company wanted to know how many do I need so that I can satisfy demand. And that was the beginning of performance modelling based on Markovian systems. So we've seen that the size and complexity of systems means you don't want to do this by hand, so we use formal techniques and automatically generate CTMCs with languages like Pepper. So why does this not satisfy all my needs when I come to collective adaptive systems? Well, there are certain key challenges that really make Pepper unsuitable for doing this. So one is openness and the rich forms of interaction that we get in these systems, and I'll explain each of these challenges in a bit more detail in a moment. Another is influence of physical space. So we had a model with the active badge example where we had physical space, because we had the 3 corridors where the person could move, but we just represented it informally by encoding it in the syntax. And quite often, if you think about sensor networks, who they can talk to depends on their distance. So we need to get a lot more serious about physical space. And then capturing the adaptivity is something else that we need to do, which is quite difficult at the moment. So we say that Pepper is a conservative language because it has a sense that agents are just there in the system. We design the system with Pepper, and we have those components, and they stay. Now, sometimes they may reach a deadlock, so they may no longer have any further behaviours, but the components that we start with in the system equation are in the system for the whole time that we're modelling it. And this is not the case with many collective adaptive systems, because agents will come and go, perhaps through faults, perhaps they will be damaged, or maybe the network gets separated, or then by choice they may disconnect. So we see this with peer-to-peer networks, that actually the behaviour changes because somebody just chooses to disconnect and they're no longer serving as a hub in the network. So we had a kind of openness that agents within the system are coming and going, and Pepper just can't do that. We have to have everybody who potentially might be there in there from the beginning, and that makes our systems bigger if we have lots of redundant ones there just in case, or it restricts us because we get to the point where we haven't got enough agents to actually model the system. The other problem with agents coming and going is the Pepper style of communication is a named channel between two agents, and so it assumes, and it's blocking. So, you know, if I say that Juliana and I have to cooperate and Juliana leaves the room, then I'm stuck. I can't do anything. And that's just not suitable for these kind of open systems where partners are coming and going. So we need non-blocking communication. Generally, we need sort of richer forms of interaction. So these are maybe asynchronous communication. So a classic example of a collective adaptive system that has this is social insects such as ants, where they have a collective behaviour that they send some out to forage and then they learn where the food is and the rest go, and so you've got an emergent behaviour comes out because pheromone trails are left and other insects later come along and find this and can follow on. And so that's a very asynchronous form of communication, which again is completely different to Pepper. So there are some languages, there's this one from Italy called Scale, which offers very rich forms of attribute-based communication. So each agent, as well as having a process description, also has a knowledge store, and it has a lot of reasoning it can do in its knowledge store. So we wanted to look at something like that, but the difficulties is we're still trying to do quantitative modelling. So we don't want our state spaces to become huge. If you have an arbitrary knowledge store, each state of the knowledge store is an additional state of your agent. It's an additional dimension to the state of your agent. So if you had 2 states, but your knowledge store has 10, you've suddenly got 20 states in your system. So we have to try and be circumspect in terms of what knowledge we capture. As I already mentioned, location and movement are often important, particularly when we look at applications like smart cities or smart buildings, and we can represent location implicitly, as we did with the active badges. But that seems unsatisfactory. It would have been much nicer to be able to specify that random walk by saying, randomly choose one of the locations you can move to. And that makes your model a little bit easier to specify when it's very complicated. And so we want to move to having modelling space much more explicitly and being able to make our sort of knowledge of the geographical world work for us in building the models. I'm not going to say too much about that one. And then the final one is adaptivity. So our process algebras, we saw with Pepper, have a very fixed set of actions. So we specify at the beginning, these are the actions, these are the rates at which they'll take place. We did have the possibility of perhaps making some of those rates functional. I didn't show an example. But there's not really a general idea of adaptivity. For that, we would probably need to have goals and objectives. The language karma goes some way towards that. With my PhD student at the moment, we're going a little bit further, where we're building in kind of having objectives specified in the karma model, and then policies that will adapt the rates to achieve those objectives. But that's still very current work. So karma. As I said, it's collective adaptive resource sharing Markovian models. It's a process algebra style language, so it's very similar in its fundamentals to Pepper in that it has actions and processes, but it's much more complicated as well in that it needs to have this idea of knowledge or stores as well. So we have behaviours of agents and their interactions. We have a knowledge in the system, and the knowledge is both at the system level, so we have some kind of global knowledge about how the system is, and each of its agents also can have knowledge or attributes. And then we have an environment in which the agents are operating. So this means that we can describe a system and then just drop it into different environments and see how it behaves, which is quite useful at times. Our environment can take account of the open-endedness, so the environment can change what agents are present in our system, adding them or deleting them. And it can take account of resources, locations, visibility, etc. So it's actually the environment that sets the rate at which things happen, which gives us that adaptivity, because it can see, for example, if the roads are very congested, the taxi's movement will be slower. So collective adaptive systems have two interaction patterns, which are, one of which is quite different to what we have with Pepper. So in particular, we have an idea of spreading or broadcast. So we have one agent who has some information or wants to request some information at the same time from a group of other agents. So this is the case that here we have the green guy who wants to share the information he has, and he sends it simultaneously to all the other agents. And then they all have that information. Now with Pepper we just couldn't do that, it just wouldn't work in quite the same way. And the one that's closer to Pepper is the idea of collecting, where we have one-to-one interactions. So in this case we perhaps want one agent to change its behaviour according to data collected from one other agent. So now we're looking at the green guy. He's got potential interactions with the ones with red, yellow and blue letters to send. He chooses one of them, receives that, and will alter his own behaviour on the basis of it. So we're working now with this idea of a collective. So our system is a collective. So in some ways it's not that far different to what we had with the system equation in Pepper. We've got a whole bunch of agents. But we particularly say now that they're enclosed in an environment, and the environment gives rules to the possible interactions, which we didn't have with Pepper. And then we have attributes. I don't know how well you can see, they're wearing different coloured trousers and tops and hats. And so this is how we actually reference our agents. So there's less focus on their names and more on their attributes. So when we want to communicate with someone, we say, I want to communicate with someone with a red head. So the system, the Karma system, consists of the collective, which is a whole bunch of agents operating in an environment. And the collective is a set of components, so each one of those guys is an agent, and it has, they can interact with each other, and this is really the behaviour that we see in the system. So just as we have in Pepper, the real behaviour comes from the interaction with the agents. But we have the environment which then imposes certain constraints on that. So the only kind of environment we had in Pepper were the cooperation actions in the system equation. They told us when agents had to synchronize with each other. But now we can tell agents perhaps to switch off certain actions. The environment might say the rate of the actions. So there's a lot more that the environment does. So this is one of our agents. Okay? And just as with Pepper, he has a behaviour which we specify as a process. So here he's got some start state, a number of transitions coming to an end state. But additionally, he has his idea of knowledge. Okay, so to introduce the terminology we use, we told this. So each component or agent has two parts. It has a process specification, which is pretty much like a Pepper specification, saying what states you do, what states you have, and what actions move you between them. But then it also has a store, which is your attributes, and we call this whole thing a component. So these are components. Formally, we say the store is this gamma, and P is the process. And the store is actually a mapping between attributes and values. So we say what form the store has, what attributes it might have. So in my little graphical example, the attributes were trousers, tops and heads. And then we had different values according to red, green and blue. And so this is the general kind of idea. And so when we identify who we want to interact with, we do it by predicates on the attributes. So you identify, I want to communicate with somebody with a red head, and it's not just it's not as simple as that, because the person with the red head might say, I only want to listen to people wearing a blue shirt. So we have two predicates, both the sender and the receiver predicate, to filter messages. So we have a bunch of agents here, so we've got different poses and different colours. And one of them might say, I want to unicast, I want to have a one-to-one interaction with someone who's pink and looks like this. Well, in this case, there is only one potential. He doesn't seem to have any predicates, so then they interact, and he now will change his state according to the information he received. In this case, I've chosen to make him blue. If there are multiple candidates for the interaction, for the unicast, he'll just pick one of them, and in this case, he's changed it to green. Okay, so that's the kind of idea that we're selecting by the predicates of who we want to. So this is what we call attribute-based communication. So we have different forms of this. So we can have an output and an input, according to whether agents are going to be senders or receivers, and we can have broadcast and unicast. So with the broadcast, a message is sent to all components that satisfy a predicate. And with an input, a process is willing to receive a broadcast from anyone who satisfies its predicate. So I say there'll be two predicates typically at play. So filtering both who you send to and who you receive from. Unicast is similar, but we're now always looking at one-to-one. So with the broadcast, it may be that if we just briefly go back, this has been a broadcast. Oops, this one. I could have simultaneously sent to all of these. They may or may not have received it because we assume that communication is not perfect. So the environment will tell us whether they really received it, but we have potentially the possibility of updating all three at once. But so we have unicast is strict from one-to-one and broadcast is not. And broadcast is also actually non-blocking, so if there's nobody that matches my predicate, I just say it anyway, and it's gone. In all cases, the actions are exponentially distributed and, as I previously mentioned, determined by the environment. So formally, the syntax gets a lot more involved than it was in Pepper, so I'm going to go through it quite slowly. So in each case, we have an action type, just as we had with Pepper. So we had alphas before to tell us what type of action we're doing. And we just decorate the broadcast ones with stars because we really need to know whether this is a broadcast or a unicast. We have the predicate on both the input and the output because we're selecting who we want to hear from or talk to. And then we have the option of, well, let's just go back there. These are passing variables. So when I broadcast something, I am telling you something. And so I can send some values and then there are some parameters here that may be updated on the basis of the information received. And the effect of that is this sigma, which tells you how your local store, your local knowledge, or your local attribute values are updated on the basis of this action that's taken place. And we'll see an example in a moment. So after the execution, the process can update the store, and it's not necessarily a deterministic update, it may be a probability update. So for example, if we're modelling a random walk, we might have that we broadcast that somebody should move, according to some predicate, we send a value v, and afterwards the position x is the previous position plus a uniform distribution over -1 and +1. So we're not actually committing in this action what it is. It's really a random walk. We're saying you just should shift yourself left or right after you receive this message. And so it's quite a different style of modelling to Pepper. With Pepper we would have modelled this explicitly as a choice of you might receive this message and choose to go left, you might receive this message and choose to go right. So when we have processes, a component may actually have several processes inside, but they just run in parallel with each other, but they can communicate via their attributes. So one might update an attribute that then influences the other, and all updates are assumed to be instantaneous. So really there's just one duration. It's the action that happens, say a broadcast, and then the update happens, and then time starts again. So They can also depend on the values that you receive. So for example, we may say, I want to broadcast, or I want to receive a broadcast only if value x is greater than 0 and the trust level is less than 3. So that's saying who I want to hear from. I only want to hear from you if your trust level is less than 3 and the value you send me is positive. Okay, and then I update my stuff. So here we've got 4 components in parallel. Okay, so this is 1, P, Q1, Q2, and Q3 with some different possible actions. So P in particular wants to make a broadcast output. And it's saying he'll talk to anyone whose battery level is less than 5%, and he's going to send a value B. And currently his role is master. Okay, so we need to look and see who might receive this message. So when we look, we have 2 possibilities. This guy, Q1, will receive message from anyone whose role is master, and his battery level is currently 4, so he satisfies the case here. This guy would only talk to someone who's super, so he's not going to listen to this broadcast. And this one really doesn't care. He'll just accept a message from anyone. He just says true. But again, his battery level is sufficiently low. So we've got 2 people who might receive the broadcast. And in this case, we assume that it's successful with both of them. So afterwards, he's just updated that he's moved on here to his new knowledge store. And here we've substituted the value B for the variable x in the 2 that receive the message. So we can have the case here where, again, he just stipulates he wants to talk to people who have battery level less than 5%, and in this case nobody satisfies his condition. Okay, because this guy's going to go with battery level less than 5%, but he'll only talk to supervisors, not to masters. And so in this case, he just sends it out into the void, and so this is the non-blocking communication that just goes on. And then finally the unicast. So now we have P wanting to send a unicast stop, again, only to people with battery level less than 5%. He doesn't send any value in this case, and his role is currently master. He's got 2 potential partners for the communication, but only one of them can partner with him, and that will be chosen probabilistically. In this case, we assume he's actually partnered with this guy, and so we see the update here. Okay, so there's these different predicates playing roles, so it's a much richer form of interaction. You can encode much more in the processes. We also have this environment, and it's the environment is not intended to model centralized systems, but it gives us the context in which our model runs. So for example, it can influence the interactions between components. For example, if you were looking at wireless interaction, a very thick wall might make a difference. Component, there may be a notion of how far distant things can be to affect communication. And so we put that into the environment. So it's the intrinsic rules that govern the physical context. It consists of a pair, again, of a store and, in this case, a function. So the global store has certain knowledge about the system, and the evolution rule tells you how components are allowed to be updated. So the easiest way to show you the evolution rule is to start with a small example. So in this simple case, we assume that we have some taxis who are moving around in the city trying to pick up users. And both the taxis and the users will be modelled as components in this case. The city has been subdivided into a number of patches, which are arranged in a grid over the city. In this case, there are just 9 patches. Users will arrive randomly at certain patches, and then their rate of arrival will depend on what time of the day it is. So, for example, we're going to assume that In the morning, people want to travel towards the city centre. In the evening, it's the reverse. When a user arrives in the patch, it makes a call for a taxi and awaits where they are until a taxi comes to pick them up, and then they will move to their destination. Taxis that don't currently have a fare may move to the patch where they see there's a call. So the idea is that the taxis are almost scavenging, trying to pick up where the users are. So they use this information of the call to choose where to move to. So we have taxis and users as components, so they each have to have a local store. This might seem quite abstract, but I think when you see the attributes, it will make sense. So for a taxi, there are three elements rather to their local store. They have a location, where they currently are. They have the occupancy, which is whether they've currently got somebody in the taxi or not, so whether they're free or occupied. And then we have a destination of where they're travelling to next. Okay, so these can each have values. Under the users, they just have two attributes. So they have the location, which is their location where they currently are, and the destination they want to travel to. And then for the users, their process is quite simple, as it was described. They have a local state waiting, where they will broadcast a call, which they're happy for anyone to receive, so they've got no predicate on that. But the content of the call is their current location, given us an XY coordinate, and then they just go back to wait. Or they can do a take, which is a unicast action, in which case they will only talk to taxis that are where the location of the taxi is their location, both X and Y. So in other words, they can only be picked up with a taxi that's right there with them in the same patch. They send their destination as information with this unicast action take, and then actually they are killed. Okay, so it's a rather drastic taxi company that they kill their passengers when they get in the car. Just from our point of view, the users only serve to create demand for taxis. Once they're in the taxi, we don't care about them, so we get rid of that process. So this is the thing that we couldn't do with Pepper, because we'd still have to have that person, and then we would have to do something to make them become a fresh user at their destination or something. Here it makes much more sense. All their role is to send a taxi somewhere. Once they've done that, this agent disappears from the system. For the taxi, it has two states, F and G. So F, I think, was originally foraging and G is going, but they can receive a broadcast call, and if it's not their current location, so the message that they would receive, with X and Y, they set their destination to being where the call came from. So they're going in search of passengers. Okay? And so they change their state to going. So they're no longer receiving calls, they're going to go off and chase this passenger. Might not be the smartest tactic, we can look at the results, but this is what these taxis do. Or they can pick up, they can receive a take action with a certain position, X and Y, and that will only have matched if that's the same as their current location. Remember what the user said, and it receives this destination X and Y and changes the occupancy to 1. So even though the passenger's dead in the back, they consider themselves occupied. When they move, this is an unusual one. So this is saying I move, I send a broadcast message, but I have a false predicate. So does anyone think why we might want a false predicate? So if true means I can match with anybody, what does false mean? Yeah?
Just that no one else needs to move.
Exactly. It's just something you want to do privately. Okay, so this is the way we call it a spontaneous action, but if you have a false predicate, nobody can match with you, you just get on and do this. So when he's driving, he's not going to receive any more calls or anything else, he's just driving to his destination, so he has a false predicate, no data, but he sets his location to be the destination, and the occupancy to be 0. So that's the process. So I have one other form of component, which is something I call an arrival. And the arrival process has a single attribute, which is location, and its process just says that it has a state A. In that state, it does one of these spontaneous actions, so it just does an arrival by itself and repeats. So we'll see quite what this is used for in a moment. Okay? So it's executed in a separate component privately. And the location attribute just says where the user is going to arrive. So it's assumed that all the actions in karma take some time to complete, and that's an exponential distribution. But you'll notice that actually when I was describing my components, I said nothing about those rates. There's nothing about rates there, there's only actually the logic, the capability of the actions. That's going to be determined in the environment, and also in the environment we have this notion that communication may not be perfect. We can decide in our environment. We may say all broadcasts are always received by everyone, or we may say only 80% of them are successful. So it just lets us play with different aspects of the model quite easily. So the way that the environment manages these things is this function called the environment rule. So this is actually a function with 4 different parts, and it's a bit complicated, so we'll go through them one by one. So one of the things to note that it may depend on the current time, and you got a hint of that when I said that the taxis behave, or the arrival process behaves differently. In the morning, people go into town, in the afternoon they go out. So there's a dependence on the time there. And then we have these things which are called the evaluation context, so we can choose the probability for a given sender store and a given receiver store and a specific action type, what's the probability that the message will be received for a broadcast. Similarly, we have a notion of weight with unicast, which is the way that we choose which of the possible unicast partners are going to be the one that we set up. We have this execution rate, which tells us if the component has a certain store S and it's doing an action alpha, this is the rate at which it happens. And then we have what we call the update, which is the thing that alters what agents we have in our system. We saw how we kill things. This is how we make new instances. It looks horrible when you look at it like this. We'll look at an example and it looks slightly better. So this is the probability of broadcast actions being successful. We say, so in any state where we do a call, then we just set the probability that it's successful to be this global.p lost. And we can set that in the environment, so we just have, say, 10% of the broadcasts get lost, or we can change it to be 50% and see how the system behaves in these different environments. Okay, so they're all set as little functions like this, and they have a default that if you don't bother to specify it, it just will be 1. So all probabilities will be 1. So we're only assuming that the call is, the broadcast is a little bit unreliable, as you would expect. For the unicast actions, we don't use explicit probabilities, we use weights so that we've always got a probability distribution. And here we just alter the probability that you're the person who takes. Depends on how many taxis there are. So if you're in a patch with 2 taxis, there's a 50-50 chance that you'll be the taxi that gets the customer. If you're in a patch with 20, there's a 1 in 20 chance that you're the one that gets the customer. So that's what this is saying. And then all the other probabilities are just weights. Just take it to be 1. And then the rates we set up like this. So this first one is just saying true, so I can actually change depending on the state of the system. In this case, we're just saying for any state of the system, tape has a set rate, call has a set rate, and then this is where we see the timing dependency. Move is a function of time, depending on now and the locations, and arrivals similarly depends on the current location. So these depend on time, reflecting the shifting patterns of traffic. Okay. And here's where we see our arrivals. So we had that process that just spat out arrivals every so often. That's all it did. It just did the action arrival. But when we see the action arrival, the effect within the environment is to create a new user with the sender location, so where the arrival has come from, and the destination location, depending on the time and the sender location. And it starts in the state wait. Okay, so this is how we create the new ones. So we kill old ones, and then we use the environment to inject new ones. So once we've picked up a customer, they sort of disappear, and separately we have an arrival radius spawning new customers for us. So this specifies the full behaviour of our system. We also have to say what we're interested in to measure, because it's a much more complicated system than a Pepper model, where we just tend to look at the throughput of all the actions, we look at the utilisation of all the components. So here we explicitly measure them. So we might say, I want to look at the number of waiting users in the patch 0, 0. Okay, so I define this as my waiting users, the number of users in the state wait where the location is 0, 0. We might look at the number of taxis that are relocating. So this will be the measure of the number of taxis that are in the going state where the occupancy is 0. So they're not carrying a passenger, they're just moving around scavenging for future passengers. Okay, so we can take our system as we've described it and put it into two different environments which correspond to two different scenarios. Okay, so we consider a 3x3 patch with locations I and j, and so where I and j are between 0 and 2. And then we have the first scenario where we say, well, users just arrive in all patches at the same rate. Or the second one, we say, at the beginning, users arrive around the periphery, and then later, when we switch, they arrive in the centre. So the pattern that we suggested that they're moving. So this is just a matter of taking the same collective and dropping it into different environments. So our collective is a set of arrival processes, one for each grid. So this is a kind of matrix array notation that just says make an instance for each possible combination of these. And similarly, we have taxis in each grid location. This is the destination where they're not really going anywhere, and then this is they're starting in the free state. So Karma has an operational semantics. As you might imagine, it's much more complicated than the simple SOS rules I showed you for Pepper, but it does have a similar set of rules which fully specifies how to get a continuous time Markov chain from any model that you write down. In theory, these could be modelled by numerical analysis with the Q matrix and linear algebra. In practice, Karma models it's very hard to keep them small. As you can imagine, once you've got attributes as well as process states, the state spaces get very big. So we tend to use stochastic simulation, and we also have just developed at the moment but not publicly available a fluid approximation as well. So we're just going to show stochastic simulations. So this is the first scenario, and we're looking at the average of number of users waiting at 1, 1 and 0, 0. So 0, 0 is a peripheral square, and 1, 1 is the central square of our grid over the city. And you can see that the users are typically waiting much longer in the centre than they are, or there's more users waiting in the centre than there are around the edges. Okay, so it's in the first scenario. And we can see that the taxis are actually spending a large amount of time relocating. Okay, so they're chasing the way this is set up at the moment, every time a user calls, any taxi that's free is going and trying to engage it. There's a few that are free at each of these locations that we're looking at, and there would be at the others, but nearly half the taxis are spending their time just driving around chasing customers. So after the initial startup period, about 2.5 are waiting for a taxi in the peripheral location, but only 1.5 in the central location. This sort of makes sense. When everyone from the periphery goes into the centre, there's obviously going to be more taxis there to pick people up. So yeah, sooner a large fraction of taxis are able to collect there, and a large fraction of taxis are continually moving around. When we look at the second scenario where we have this shift according to the time of day, at the beginning we have a similar pattern that we have a lot of users waiting at the edge, but then actually as users start to arrive more in the centre, we have a larger number waiting in the centre and fewer waiting at the edge, because we've shifted where the users are. And so this becomes actually a much more balanced system, that they're not waiting particularly longer in the centre. And if we see the pattern for the taxis, we see originally it's pretty much as before, but then when the demand changes, the number that are having to relocate is changing as well, because we have a greater number of people arriving in the centre where you've got more taxis, because they're still coming from all the peripheral edges. Okay. So we have two different parts of this trace. The first from 0 to 200, 3/4 of our users arrive at the border and only a quarter in the centre, and then we shift so that we have a quarter arriving in the border and 3/4 at the edges. I don't know why it's wavering around so much. So we can see that we get a much better balanced system, and we could look at perhaps altering the behaviour of the taxis, that they don't chase jobs so much in the early part of the day, because obviously it's not good behaviour. Okay, so to just make some conclusions about this, collective adaptive systems or collective systems are certainly an interesting class of systems that need to be modelled, because increasingly they're kind of present, but they're quite a challenging system to design modelling languages for, because of the complexity. So their role of infrastructure, as I said previously, makes it really important that we do fully understand their behaviour before we deploy them. I think it's really incumbent on us, when potential users may be unaware that they're under the influence of systems, to make sure that those systems are correct and timely. But it is difficult, and I'm getting a lot less smiles in this one, so I think Karma is a lot more complicated than Pepper, and I will fully accept that. But it has tried to address the challenges. It's very much a language still under research, and we're investigating the possible uses for it. It's been used recently for looking at fog computing, so having users that are at the edge of networks and may transfer their use. And certainly this was done by researchers in fog computing, and they were very happy with Karma, because it allowed them to build very large Markovian models that they couldn't build by hand, but they had a lot of faith that they were doing the right thing, because it was in a formal language and we could do certain checks on it. So it has these much richer forms of interaction with many predicates, and I would say that's one of the strengths, but also one of the fallbacks of difficulties of using Karma, because actually understanding the interaction of all these different probability distributions, that the sender has their predicates of who they will talk to, the receiver has predicates, the environment sets probabilities on that, and then the updates have probabilities too. So it's not always easy to understand what exactly is happening in your model. And I must say, when we model ourselves, we tend to set a lot of probabilities to 1, because it makes it a lot easier to understand. So sometimes I say this is still an experimental language, and I think we'll probably make a new version that's not quite as strong, but easier to use. Fluid approximation is something that we want to do here. As I said, it's not yet included in the tool. We do have a theoretical result and a paper under submission at the moment, but it's complicated, because for fluid approximation we need to be able to ensure that we have certain proportions of behaviour, and when you've got the attributes, you're kind of splitting your populations. So we have to impose some quite strong conditions, particularly with respect to broadcast, but so we do have the theory in place now. So thank you very much. This is very much quite recent work. It was part of an EU project called Quantitative, and all the work on Karma is joint with my collaborator Michele Loretti. There is a tool, another Eclipse plugin, It doesn't have the fluid, but it has the stochastic simulation and numerical solution. So if you go to the Quantitative website, you can access the tool and play around with Karma. And we're particularly encouraging people to play around with Karma because it's really useful to get feedback. So thank you.
Questions?
Sorry. In the interaction model, interaction paradigms between agents, we talk about broadcast and unicast communication. I would like to find out whether it is possible to communicate, to do multicast instead of communicating to everyone or to just specific agent. Is it possible to communicate to some members in the group instead?
So that's what's intended with the attribute-based.
Jane, can I interrupt? Could you just repeat the question?
Oh, sorry. There's a weird disembodied Marvin in the room. So the question was whether it was possible to have something between the unicast and the broadcast that was more like a multicast. And I was just going to explain that that's really the intention with the attributes. So the broadcast, because it has the predicate of certain people that you consider valid receivers of the message, it's not true broadcast. If somebody doesn't match that predicate, they cannot receive your message. So it is multicast in that the predicate allows you, or the attribute lets you choose who your multicast group is. So we call it broadcast to really distinguish it from unicast. But unless you set your predicate to be true, it's not a true broadcast reaching everybody.
Any further questions? Marwan, is there questions down there?
There were a few frowns down here.
Make them turn that frown into a question. No?
None down here.
Okay. Anyone else here?
I think everyone wants lunch.
I think everybody's tired by now, yeah. But remember, did you sign up for this lecture now again, swiping? You have to do the same thing when you come back for the afternoon. And maybe you'll be refreshed from a bit of sunshine and a bit of fresh air as well. To actually be full of energy for the next one. Yeah?
So the next one is completely different. So.
Yeah. It touches on machine learning. I know lots of you are interested in that, so that would be maybe something.